producer, consumer, read-only, and all those kind of patterns. The streams are actually spread across the course, and there are a lot of opportunities. Like the hardcore preachers are able to train their own streams based on this. They are able to train the streams which are spread across the course. So in this paper, what we have done is we have proposed a streaming technique, which is an idea where one prefetcher tries to communicate its own stream to other prefetchers, so that the prefetcher, the entire core, like a per core prefetcher will try to prefetch for its own core, but at the same time it will communicate to other cores also. So in this way, we are able to get around 11.3% improvement in core code and 9% improvement in main cores with additional overall less than 3 kg. So some diagram of streams. So stream is nothing but a sequence of place and line memory addresses. It's like textbook mechanisms. So there are prefetching techniques which exploits different kind of streams, like temporal streams, which are sequences of addresses which correlated in time, but they don't correlate in space. There are techniques for DNS. Then for spatial streams, which are correlated in space, it's good for like fixed data layout like arrays and all. And the combination of these two structure control streams, so there is a technique called streams, which try to find out the correlation, temporal correlation among the spatial regions, and then find a spatial correlation within address space, like within a region. So, an example, so in this case, as you can see, the address A plus 2, A plus 3, and A plus 7, all these are correlated in space, meaning we have started with the base address A, and there is an offset of 2, 3, and 7. So, as I mentioned, so these are pretty, it's pretty dominant in like fixed data layout data structures. But as compared to spatial streams, there is something called temporal streams. As you can see here, A, B, and C, they are not correlated in space, but they come in a cluster. So there is a correlation in time. So, point of the import is a good example of temporal stream. The focus of this talk is on spatial streaming and how to make it aware of the cross-core streams which spread across multiple cores. Before that, basic understanding of a state-of-the-art spatial memory streaming technique, which is called SMS, and how does it work. So what it does, it divides the entire system space, the memory space, into fixed type regions, and each region consists of a bit vector. So this region is identified by a signature, similar to any previous technique, and each bit in the bit vector corresponds to a case line. So it's very simple. Memory space divides into multiple regions. Each region has a signature. Signature consists of a bit vector, and each bit in the bit vector is a case line. So let's go through an example. So there is a miss to address A plus 1. So what SMS does is it filters the tag path, which is nothing but the MSC part of the address, and it has another attribute called PC/object, which is nothing but the signature for a particular request. So in this case, the tag is A, and the PC is nothing but the program counter corresponding to this address. So in this case, we have assumed the program counter for this request is PC itself, and offset is 1 because if the base address of the region is A plus 1 will have offset of 1. So continuing. So let's say sometime when we start say plus 3, what SMS does is it tries to populate the bit vector. Remember, bit vector consists of the cache line, so it is a cache line. So here again, the tag is same, PC and offset is same, but now in bit vector as you can see, so in this case I have assumed a bit vector of 4 lines, that means a region of 4 cache lines. So the second, so the first and the third bit is same. So it's a bit vector of like 4 bits, 0th line, first line, second line, and third line. So as you have misses to address A plus 1 and A plus 3, so the first bit and third bit is set. So continuing like that, now the miss to address A plus 2, so now 0 followed by 3 ones because A plus 1, A plus 2 and A plus 3 are getting misses. So these two tables combined together is known as active JSON table. This is logically implemented as 2 tables, but physically it's actually one hardware table. So this training process continues unless there is a eviction or invalidation to any address which belongs to that particular region. And in that case, it transfers the trained signature. So in this case, it transfers the signature along with the bit vector. So this bit vector contains 0 to 1. Meaning, in the future, if there is a miss to, let's say, signature PC/1, it will prefetch for that particular region's address, it will try to prefetch second, third, and fourth line, as in the A+1, A+2, and A+3 line. So this is a baseline organization. It is similar to Intel Core i7 series, so like multiple cores, private level and L2 cache. So this SMS prefetcher sits beside the L2 cache, and this SMS prefetcher, and all the cores share the last core cache, and we have on-chip memory controller. So to start with, what is this cross cores cluster streams? So in the x-axis I have taken notion of time, and the y-axis is nothing but demand misses. So let's say there are misses coming to core 0, and these are like C, D, E, and H. Similarly to core 1, and let's say continue like that. So intra-core streams which recur within a core, as you all know. So in this case, you can look at E and H, it recurs in core 0, and similarly F and G, it recurs in core 1. But there is something interesting about the stream which is created because of these two addresses, A, B, C, and D, which are spread across two cores, core 0 and core 1. So this is lost opportunity which most of the present prefetchers they are able to train themselves, and that's what we define as our expose streams. So these are the streams that spread and recur across multiple cores. So let's go into the prior works. So there have been like 4 or 5 works which are related to streaming, and it's not like cross-core streaming is a new topic to work on. So there are papers like KMS, STAMES and all, but in most of the cases, if you look at the first 3 rows of this table, the hardware overhead for a 4-core CMP is in like MBs. Like if you look at the first 50 KMS, it takes around 24 MBs, which is kind of impractical because the last of the cache itself is around 8 MB. Then we look at a technique called SMS, which is the passive memory streaming technique. It performs well, but it's not aware of the cross-core streams. So what we have done here is we have taken the SMS technique and we make sure that the cross-core streams are also available for the prefetching purpose. So here it is, extreme, where it's out of the cross-core stream, and the hardware overhead is the overhead of SMS plus around 50 kb for the entire chip and not for the core. So it's like a 4-core CMP, there is a 50 kb overhead, which is okay. So I've talked about signatures, the PC/offset. So what we did, we looked at the behavior of the signatures in PACT benchmark and for a 4-core CMP. So what we did, we tried to find out what fraction of the signatures are actually getting across multiple cores. And as you can see, around 80% of the signatures they recur at least in 2 cores. There are exceptions like swaptions and carrying also. In carrying, almost all the signatures spread across multiple cores. So then we looked at something interesting. So it says for demand this at the L2 level, like who are the respondents? So for a given miss at the L2 level, the miss can be responded by L3 cache, the last one cache, or from the remote cores, or from the DRAM. So this is a distribution of responses for a given miss. And it turns out 90% of the time the response comes from the last cache or from the DRAM. So if you go back to the previous plot, it says 80% of the signature actually share or recur across multiple cores. But it says for a given miss at the MLC, that's L2 cache, 90% of the responses are coming from large level cache or from the DRAM. So the obvious thing to do here is just increase the cache size of element L2. So that's what we did. We increased the size of element from 32 KB to 128 KB. And this is on top of SMS. And it gave around 1.8% improvement in execution time. We did the same thing for L2. So 256 KB was the baseline L2 cache. We increased it to 1 MB and it gave 8% improvement in execution time. But then when you compare us at the extreme, it gave 11.3% improvement with only around 50 KB of overhead. That's for the entire chip. It's not for core. So with this, couple of observations. First, as I have told, 80% of the signatures are actually spread in across multiple codes. This observation is interesting because this number is pretty small to store the information. So 4068 signatures are actually recorded in PACT. So you can create a hardware table to store these signatures and train themselves. The last one, all the signatures they spread or they recur at a distance of 30,000 cycles on average. That means there is a gap, the recurrence distance is huge. It gives opportunity to communicate your streams from one prefecture to another prefecture. But this number is average. It might happen that the stream is recurred in another core within 0 cycles also, like two cores are trying to occur a lot and all those things. And this number goes up to 1 million also for some of the applications. But on average, the number is 5,000 cycles. So, extreme, as I have discussed, it's a technique where one prefecture communicates its stream to another prefecture. And the core which communicates, we have named it as master prefecture, and the core which consumes, we have named it as worker prefecture. So, we can correlate to it as producer consumer prefecture, where the core which communicates the stream is the producer, and the prefecture which consumes the stream is the consumer prefecture. And this communication happens just in time. So we have made sure that the communication happens in a manner so that the stream will reach the other core's prefecture in time, not later, because it will create issues like cache collision and additional consumption. And extreme is not a data forwarding technique, meaning in data forwarding technique, when a particular core demands the data, it also forwards the data to other cores. But as we have seen, there is a huge gap between the recurrence of those streams. So even if you forward the data, it won't be of use. Similarly, it's not an intercore prefetching technique, meaning here the prefetcher doesn't prefetch for other core. It just communicates the stream. The prefetching will be done by that private core itself. So it's not changing the prefetching strategy itself, it's just communicating. It's like giving hints to a particular prefetcher. So then we try to find out what is the scope. So we try to simulate what we call the ideal extreme. Here we have indexed all the latency numbers, like we have assumed that all the its communication latency will be 0 and we don't have any limitation in hardware overhead. So we have trained almost all this special signature, we have communicated all the streams across the core in 0 cycle just to see up to what extent we get in terms of speed up. So these numbers are around 23% and 19% for 4 core and 8 cores. And there are cases like swap zones, black zone and all, where black zones is a particular case where there is data for the application, there is no communication and we are able to find an improvement even in the ideal case. So with this motivation, I jump to the working principle behind the technique of extreme. So it works in 3 steps. In the first step, we try to identify the cross-core signatures, and then we try to find out the master and the worker, the producer and the consumer. And the second step, we try to find out the recurrence distance. After how many cycles the stream will recur in the consumer or in the worker core. And third, it actually communicates the stream, like the master will communicate the stream to the worker stream based on the time which was predicted in step 2, but it is that we have called just-in-time communication. So in the first step, as I have mentioned, it's a training process. So it tries to find out what are the signatures are actually the cross-core signatures. For that, we have used a hardware structure called extreme detector. So it sits beside the last double cache, which is spread across all the cores, and it looks like this. So it has signature. So signature is nothing but PC/offset, and it has k number of entries, where each entry consists of a bit vector. So the notion of bit vector is it consists of the cache line, where each bit is a cache line, and there is attribute for a time which stores at what time the bit vector is inserted into this hardware structure. So remember, this extreme detector is placed beside the last double cache, and all the prefetchers they communicate their bit vectors to this detector. So this time field will once communicated to bit vector. And then if this was done, it says whether this entry has already participated in the detection process. So for example, for signature of PC/1, the bit vector is 0 to 1, and at time t, port 0 has communicated this bit vector to extreme detector. Continuing with our enhancement, so if you remember, the per core SMS technique, it has a table called pattern history table, which consists of the signature and the bit vector. We have extended it with 3 additional attributes. The first is worker. So once a particular signature is trained, the master should be able to find out in which core the stream will recur. So the worker will say the core ID of the picture is the signature will recur, and after how many cycles, that will be given by the time field. And at last the field coordinate, it will say whether the master has intersected the communication. So for an example, let's say previously the contents of the PSP was PC/1 with 0 to 2, now it has something like PC along the bit vector, and now there is a field for worker. So it says for core 0, this particular stream will recur in core 1 after delta interval. And the init value 0, that means the communication is not started yet, it hasn't initiated. So again, going with the baseline. So what we have added here, we have added an extreme detector, which is placed beside the last loop so that every core can access it. And there is a buffer called X-buf-S. So what it does is just an interface between the extreme detector and all the cores, because there are multiple cores and multiple streams can come from different cores at the same time. So because of that, we have to buffer there. And similar to that, we have added a per core buffer, which is called X-buf-P. What it does, when the training of the signature is done, let's say the producer is core 0 and the consumer is core n-1. So the producer will communicate with the X-buf-P, which will eventually go to the core n-1 signature. So X-buf-S is an interface between the interconnect and the extreme detector, where X-buf-P is an interface between the private prefetcher SMS and the internet. And then we change the bus, which was previously unidirectional, now it has become bidirectional because the communicated streams will go to a particular prefetcher. So then the next important part is all these cores L1 and L2 are actually driven by the frequency and voltage domain, which is different from the last level cast voltage and frequency domain. So it is similar to Intel's structural processor. So the idea behind this is extreme calculates the difference in time for the recurrence of streams. So if we use the clock domain which was driving the clocks for each core, what will happen is the techniques like DBFS and all will create noise in the process. So what we have done, the frequency and the voltage drives LLC also drives all the parts of the extreme. So in this process, extreme detector and all the internet and all, they are oblivious to the P states and C states of the processor. So I go for an example how extreme works in a simple 2-core CMP. So in step 1, let's say this is our 4 zeros pattern history table, which is PSP. So what it has a PC/1, and similarly, let's say in core 1, we have the same entry for PC/1. Initially, the entries were done, the training was over, and this is the extreme detector which is placed beside the last one chat. So to start with, let's say core 0 has started its training, and now you can see there is a bit vector in core 0's PSP. The same thing will be communicated to extreme detector for the extreme detection process. So now there is 0 to 1, and this bit vector has come at time t. Continuing, let's after some time, let's say t plus delta, the core 1 communicated its bit vector. So as you can see here, the original development comes from core 1 and at time t plus delta. In the master register 0 and 1, this shows the first entry comes from So in step 3, what it does is try to find out the set intersection of those two bit vectors. Meaning, it tries to find out bit gen, which will say how many lines within a particular region were actually shared between the two cores. So this is the case. So it does the bitwise operation, and if it's yes, so it has a cross-core threshold. Let's say I am using 32-bit vector by using a cross-core threshold of 8 bits. That means 8 of the 32 bits are actually shared across the core. And if this is yes, you can see the done bit is now set to 1. That means the detection process is over that particular entry. So then next, what it does, it updates the master code saying that for your signature, the worker will be 4-1 and it will recur after delta units of time. So in the future, when there is miss to PC/1 in the master code, it will send this particular bit vector to worker code after delta units of time. So that's what the export combination place is. So in this case, the training is already over. The master knows that at time after delta units of time, the core will get misses from this particular signature. So let's say at time t, core 0 started the training process. That means at time t plus delta, it will communicate its bit vector and it will eventually go to core 1. So at core 1, what it does the same union operation of the bit vector, meaning it is nothing but the bitwise operation. So it does the union operation of what it had before and what it has got now from the master signature. So previously it had 0.0, which is meaning that first and second line should be bitless. Now it has all the ones, that means all the text lines within that range should be bitless. So the crux of this experiment depends on the export timeliness, like how accurate are these delta predictions. So what we have done, we have registers which are encoded and it stores the clock cycle in an encoded format. The encoding is pretty simple. Given a cycle number, you divide it by 4000. That is the encoded cycle number. And they are estimated to minimize the noise from the interconnect because based on the worstness of the interconnect, this number, the delta numbers can be noisy. And on an average, these estimates are accurate for 67% of the time, meaning the streams are communicated to their worker prefetcher accurately for 67% of the time. So the rest 33%, the streams are delayed because of the interconnect or because of the prediction. So we have added 3 transactions in the interconnect because we are communicating, like boards are communicating with the extreme detector and they are communicating among themselves. So the first one is X request. So this comes into picture when a particular code wants to send its bit vector and it wants to train itself. So the content of this particular transaction will be the bit vector along with the core ID. That means master core is sending its bit vector to the extreme detector. And second, once the training is over, the response comes from the detector to the master code. So the content of that particular transaction will be time field, meaning after how many cycles the worker will get that speed and the core ID of the worker. And the last one is X communication, which is nothing but the communication between the master and the worker, which consists of the bit vector and the worker is the particular stream